taking what we know about a tangent line, we're going to use point slope form in order to find this, and because at one point, at the point 1, 1, we're going to plug into this 1 and 1 for the x values, and 2 for the slope, because if you're to plug in x, if you're going to plug in 1 for x in the derivative, and then multiply it by 2, you're going to get 2. So taking this, your derivative is going to equal y your tangent line approximation is going to be y equals 2x minus 1, distributing that 2 and then moving the 1 over to get this equation. So plugging in for 1.5 in for x, your y should equal 2, because 2 times 1.5 minus 1 is going to equal 2. So this is your tangent line approximation using a tangent line. However, Euler's method is different. And so taking Euler's method, the tangent line the Euler's method approximation for this, so the Euler's method for 1.5, this is actually going to equal 2.2, and we will run through an example, just not this problem, but I will show you how to use Euler's method in using an equation. But you are to get 2.2, and the actual value at 1.5 is 2.25. So you can see Euler's method is much closer than the tangent line approximation that we just got here a moment ago. You can see how this is much closer to this than this is to this. So what is Euler's method? I've been talking about it. What is it? How are we actually doing this? So Euler's method, Euler's method is, and I'll show you on a graph, using y equals x squared in order to show you how we course correct the tangent line at each point, because we are using a tangent line approximation. We're just course correcting it. So y equals x squared, we're going to be taking our, it's a poorly drawn, but everybody gets the point. So you will be taking a point, any point on the graph, on wherever you want to start, and we've been starting at 1, 1. So we're going to take the tangent line of this, and then as soon as we move over that step amount that we want to move, then we will make that point at that step. This equals the step. And then we will actually change our tangent line now to be going with that point. And then once we reach that step, we'll go again. And as you can see, compared to the tangent line approximation, where if we wanted to find this point on the graph, it was this far apart. Now, if we wanted to find this point on the graph, it was much closer and more accurate. And as this step goes down, and as it gets smaller and smaller and smaller, and in the example before, we used a 0.1 step. This step is going to be much smaller and much more condensed. And as it gets much more condensed, your accuracy for the line is going to go up. It's not going to be exact, but it will be pretty close, because it curves with the line. It moves with the line. Because you're taking that tangent line and then course correcting it at each point. So the accuracy is going to skyrocket. So that one goes down, that one plummets, this one goes up. So if we're looking at this on just a graph to find the equation for Euler's method and how we're going to be able to use this using how we're going to use it, which is a table. Let's draw our y equals x squared, and we're going to be drawing a general equation for this, so we're not going to be using this, but just for visual sake, I'm going to use y equals x squared. So we have this, and let's say at x sub n and y sub n, you have a point. And that's the point that you're going to be starting at, or ending at. No, starting at. And you wanted to find the point y sub n plus 1. You are going to in order to find this, like we said before, you're going to use that step to run. This is how you're going to run, because you're using that tangent line as your slope, and that is your slope, but you need to be able to run a certain amount, and you're running that step. So you run the step h, and then you're going to rise a certain amount until you get to that point on that tangent line. So it's not actually on the graph, but that's going to be h times f prime of x sub n comma y sub n. And this y is only in the equation when you have a y in your derivative or in your actual in the initial equation that you're given. So this y is not always there. Just like in when you're doing the Eulers method for y equals x squared. So if you were to wanted to find y sub n plus 1, the equation for that is going to be y n plus 1. And in order to get to this point, you need y sub n in your equation, because that's your starting point, that's your base, that's where you're going to go up every single time. So you're going to take y sub n plus h f prime of x sub n comma y sub n. And this is your equation in order to find the y value for your numerical approximation on the tangent line. And so then if you were to find the x value, whatever this x value is right here, that is going to be x sub n plus h, because you're running h. You need to add that x plus that h, and then add the h to it. And this is plus 1, sorry. And so that is your x and y values in Euler's method. Now, remembering this, and I'll bring this back, we can move on to the example problem. So this is our full example. Okay, so if we're given that the y prime equals x plus 2y, and as you can see, this is not y equals x squared. It's not y equals some sort of thing. It's not the initial equation. This is the derivative. And you, on a test or on anything, you are probably going to be given multiple versions with either a derivative or even just the normal equation, and you have to find the derivative. So given that we are given the derivative, this works out nicely because we need the derivative in the equation. We don't need the actual initial equation. So I will write our formula at the top in order to find what we need to find. And because this equation has a y in it, we will be using this y up here in our normal equation. All right, so these are our equations that we're going to need as we go along. So our step in this is going to be h equals 0.1, just like I was talking about before. And we are given that y of 2 equals 3. So given this, we are basically given our first point to start at. And we want to find y of 2.4. Y of 2.4. So what is y of 2.4? Well, that's where Euler's method comes in. So we are going to make our graph, or our table, not our graph. And then we do not need to do the actual because that is not what we're finding. We're not, in some tests they may ask you what is the difference between Euler's method and the exact answer or the actual answer, but that is not what we're looking for, so that is okay. So since we're looking for 2.4, knowing that the step is 0.1, we're going to go from 0, 1, 2, 3, 4, and that's where we're going to end off. And I will show you using our equation for x sub n plus 1. So, because we are given that this is our starting point, we are given that the x sub 0 value is 2 and the y sub 0 value is 3. And you will always be given that start value. Given that start value, then we can approximate 1, 2, 3, 4 for the ends. So x sub 1 is going to be 2 plus 0.1, which is 2.1. And then we're going to go 2.2, 2.3, and 2.4. And that is the ending equation that is the ending value that we are trying to find in relation to y. So, given that, we are going to take our equation and we're going to put it in. So y sub 1 equals y sub 0 plus h f prime of x sub 0 comma y sub 0. And so in order to find this, we are going to have to find the derivative with these two values placed in. So f prime of x sub 0 comma y sub 0 is going to equal 2 plus 2 times 3, which is going to equal 8. And so then we can plug that into our equation, which is y sub 1 equals y sub 0, which is now which we know to be 3 plus our step times this value, times that value. So y sub 1 is going to be equal to 3.8. All right, and now that we know that, and now that we know that this, we can always just plug in this part into this just right away. So I'm going to flip a page and continue this, and I will write down what we need to write down. Well, actually, I'm just going to keep it like this. So we're going to do y sub 2, y sub 3, and y sub 4, which is our final, which is what we need to find at the end. So y sub 1 plus h f sub x sub 1, y sub 1. And then we plug in the numbers. But we can just write out these equations generally at the beginning so then we know what we're looking for down the road. So then y sub 2 plus h f prime of x sub 2, y sub 2. X sub 3 plus h times f prime of x sub 3 comma y sub 3. And then this will be our final answer. So plugging in the numbers, we have 3.8 plus 0.1 times 2.1 plus 2 times 3.8, plugging in this derivative down here with the equation. And then that is going to equal 4.77. And then taking these x sub 2 and y sub 2 values, we're going to plug that into the y sub 3. And so then that will be 4.77 plus 0.1 times 2.2 plus 2 times 4.77. And that then is going to be equal to 5.944. Now taking 5.44 5.944 and 2.3, we can plug this into our final equation for y sub 4, which is going to be 5.944 plus 0.1 times 2.3 plus 2 times 5.944. So that kind of gets squished at the end. And then that is finally going to be equal to 7.3625. And then, so your y sub 2.4 is approximately equal to 7.3625. And then that is your final answer using Eulers' method. So, to recap, Eulers' method is the tangent line approximation with course correction, which takes the step and then reapplies the tangent, and then takes the step, reapplies the tangent, and for that slope. And just as a reminder, your slope is going to be h rise over run, which is this, and your slope will just end up being the derivative with those two inputs. And so taking that course correction and taking that slope, you're able to put it into a table and able to approximate using our two equations from the graph to get your final answer, whatever you're looking for, which could be y sub 2.5, y sub 2.6, y sub 10, who knows, but you're able to approximate using Eulers' method, and that's how we came up with it. And I'd like to thank you so much for listening, and I hope you enjoyed this too. So, thank you.